All right, everybody. Hello and welcome back to another very exciting topic, generalization and decision making. So here we are talking about conceptually making generalizations and decisions using research. So we have another part to this, our types of analysis lecture, which should be taken together with this. You shouldn't be thinking about one without the other, because this is the conceptual overview of generalization and decision making in research, where that's sort of looking under the hood of generalization and decision making in terms of the statistics we use. But here we're talking just conceptually, all right? How do we make decisions in science, and specifically in psychology? So we have this idea here that we will talk about first, which is universalism, which is the assumption that a finding will apply to all people. All right, so take some relatively famous psychological findings. We can take something like the Zimbardo prison experiment, the Stanford prison experiment. The idea behind a study like that, right, and if you're not familiar, the study is such that individuals, young men, college-aged men, were randomly assigned to play the role of a prisoner or a guard in a simulated prison. And what happened is very quickly the guards took on the role of guards in a very serious way, including some harm to the prisoners. But the idea is, right, that a generalization was made from this experiment. The generalization being, if we put people in positions of power, they're going to act a certain way. That, of course, is an unethical experiment that we can't necessarily recreate today. But the idea of psychological research in this way persists, that we want to be able to apply phenomena from a small group of people to others. And this is imperfect. All right, it says that the principles of psychology will not vary, but we know that it can, right? We know that psychology is not completely consistent across all individuals. So I kind of gave away our last point here, right? Universalism is that psychological findings will apply anywhere and will be the same for all people, irrespective of society and culture. So I sort of beg the question here, do you believe this to be true? And we might be able to even think to some instances kind of off the bat here where it's maybe not true, all right? So this is a comparison between collectivist and individualistic societies. This is a kind of a social psychology or a sociology idea here, that we have cultures that are inherently different on a set of characteristics. And maybe you've heard these terms before, that in a collectivist society, groups are treated as greater than the whole. The self is viewed as a part of a group. And we actually see some other trends in these groups as well. I have a list here: slower pace of life in collectivist societies, lower heart attack rates, lower divorce rates, indirect communication, and so on. Whereas we look to individualist societies, where people view themselves more as individuals, the self is viewed as independent from other groups, faster pace of life, higher heart attack rates, all right, so on and so forth. So we know that universalism can't be applied as a blanket to everybody, right? Because we see these cultural divides that are pretty clear here. And I've listed a couple examples of each type of country like this down here. So you might be thinking then, okay, why are we talking about universalism if it's so flawed, right? If we can't really have universal tendencies in psychology, well, because it works in the other direction too. Sometimes we can take behavior from something even inhuman, right? Psychology is the study of the mind and behavior, and we can do that in animals as well. So sometimes this sort of goes the other direction. We can make generalizations or see universal trends in psychology by looking elsewhere. So here's an example, one of my personal favorite studies. This is using cockroaches, all right, so that's what we have here. And we have a test box or a race box or a maze box. These are used often in comparative animal behavior. And comparative animal behavior is a very interesting field because we compare animal behavior to human behavior to see if we can get to the bottom of any perhaps evolutionary trends in behavior. So taking a look at one here, we have cockroaches, and they are completing a simple maze, all right? So if you look at the figure, we have start and the goal. All right, so the goal of these cockroaches, the scientists are studying, they're measuring how quickly a cockroach will get from one end to the other of this simple maze. All right, then the experimental condition, all right, or what they're manipulating here, is they'll have the cockroach go through the maze by itself. And then in the second iteration, they'll have the cockroach go through the maze with an audience, all right? And one of my favorite terms I've ever seen in a scientific paper is cockroach audience boxes that they built into this particular study. So kind of silly, but what happened here was the cockroach went faster, performed better when put in front of a cockroach audience. All right, so this might seem absurd, right? What do we care about this? But what we care about this is that if we put humans in the same scenario, if we have humans perform a simple task in front of an audience of other humans, we see an increase in performance as well. So this is just one example about how behavior somewhere else, right, can be applied or generalized to human behavior. So that's the idea of generalization, right? When we do statistics, when we come up with a finding, we want to know who else that finding applies to, all right? In some cases, the scope will be very small, and in other cases, the scope will be very large. That often has to do with sampling, or how we sample, or who is included in a particular study. So we have a lecture all about sampling that's coming up, all right? So just hold your horses. But let's talk about sampling very broadly here first. So a sample is a subset of people, a group of people that you use to conduct a study. All right, and sampling can be done in a number of ways. We can sample randomly or non-randomly. Those are two major distinctions. But who we sample is going to have an effect on our decision making or on our results. So I have a little term here which hopefully you'll appreciate, especially since we will be participating in studies in some form during the course of this class. But that psychology is the psychology of psychology students. And this is also interesting if you go on to take history of psychology, because psychology research started on psychology students. So the general idea here is, are our samples representative of the entire population, and can we make generalizations to the entire population if we're only looking at a certain slice in our sample? So this goes back to universalism. When we take a sample, we expect to be able to make some inferences from that sample back to the population. We're assuming that there's some similarity from our sample that can be sort of moved back over to our population. But where this is an issue is sometimes samples are not representative of the population. And you've maybe heard this word representative before, and I always like to compare it to politics, right? We have representatives who are meant to represent a group of people and express those ideas to the political sphere. We know how well that works, right? It's not without error, but the idea is the same here. That we want groups of people that represent the entire population. And then we have something called a convenient sample, which is very different than that, where we just grab whoever's closest and who's available. So this sort of goes back to the psychology, is the psychology of psychology students, right? Often who's most available for research are those who are at a research institution, who are getting a degree in a research-related field. So just some food for thought, right? And thinking about when you read scientific papers, you want to know who the sample is. You want to know who those results were drawn from. So a little bit more on sampling. So you should have learned about sampling a bit in your statistics class. And again, we'll talk about it in greater depth a little later on in the class. But first, some general ideas, all right? When we take a sample of people, Generally, larger samples are regarded as being better. All right, and by better, what we really mean is more representative. Because if you think of an entire population, the more people we take from that population, the more representation we have from that population. All right, so it's just sort of a law of numbers, right? The smaller your sample, the more people you are missing. However, this is sort of a double-edged sword because a larger sample that's not representative might yield significant results, but they might not be entirely accurate or generalizable. This is a probability issue. All right, we're going to talk a lot about probability in this class. It's the basis of hypothesis testing and decision making. But probability can be manipulated relatively easily. Probability is still just a chance that something happens. So with a larger sample, we're more likely to get that chance of something happening. It's a little bit abstract, but I think that when we review p-values, it'll help to remind us what this particular function really helps us to do. All right, another type of concern that we have when we're sampling is weird populations. This is a sort of newly coined term that I think really well captures the issues that we have in general sampling in the population. So we have what we call weird populations. This is an acronym for who is the most likely to participate in a research study. All right, so the W is for white or Western. All right, and by Western, we just mean Western society. A lot of research coming from the US and other Western societies. E for educated. As previously mentioned, you're going to participate in some research this semester in some form, and you're getting educated, right? If you're being educated at a research institution, you're more likely to be aware of research, more likely to participate in research. Industrialized countries have more access to research resources than unindustrialized countries. Rich, all right, research requires money, requires that dollar. So richer countries, richer areas even, are more likely to be putting funds into research. Therefore, the population and the samples they're getting are often rich samples as well. And democratic countries are more likely to have research programs. Therefore, the samples we draw are more likely to be from democratic peoples. So this is an issue for a number of reasons, all right? We can only do research on those we have access to, and we need consent to do research on people. And the people that are often most willing to participate in research are people who understand the importance of research, and again, are those who are surrounded by research in their professional life. So that's a good thing, but it can also give us samples that are not representative. I'll share a personal example. I worked at a study at UCSD. We were looking at attachment in children. We were looking to try and compare those who were securely attached, avoidantly attached, anxiously attached. And we were looking at infants, 12 to 18-month-old infants. We started collecting data, right? We did outreach in the community. We wanted people to come in and participate. The bulk of our participants at first were people who worked at the college and who had kids, right? They said, sure, I can bring my kid in and participate in your study. But what we came to find is we were working with a very weird population. And within this weird population, we didn't have a lot of children that were anxiously or avoidantly attached to their parents, right? We were often talking about, I'll specifically speak to the rich point here, but families who were financially stable and where connection with children and caring for children was perhaps a bit easier than it is in other groups. So long story short here, we just need to know who our samples are. When we read a paper, we need to take a look at their method and determine who they included in their sample to see if their results should be generalized to greater groups of people or not. All right. So we're about to hop back into some statistics review, all right? We're going to do some hypothesis testing, all right? Some hypothesis testing review. So let's take a look. Move my head out of here. Okay, so we're talking predictions here, and you have made a prediction in this class, one that you might still be editing. But we make predictions, right? And our predictions often have a direction. So you might predict something like, let's take, I think medication is a nice way to sort of think about this. Let's say that you have found a new chemical, right? A new chemical makeup that you think is going to help people sleep better, but you're afraid that it might also disrupt people's sleep patterns. All right, with a hypothesis such that this is going to affect people's sleep, right? I don't know if it's going to improve sleep. I don't know if it's going to reduce sleep, but it's going to affect sleep one way or the other. That would be a two-tailed hypothesis. If you were working with maybe something that had already been shown to show some increase in sleep, increase in quality of sleep, your prediction would be perhaps one-tailed, that you're predicting a specific direction of the effect. So let's look at a couple things here. I want to shift us over to the whiteboard. I want to draw just a few things for us here. So it might be the case that you're taking statistics while you take this class. It might be that you took statistics recently. It might be that you have not taken statistics in quite a long time, all right? So we want to sort of just do some review here of what hypothesis testing really is, all right? So here I have a normal curve, all right? So when we're talking about data, when we're talking about a distribution of data, we often assume that it's going to be normal, that it's going to look something like this, that most of the data is going to fall in the center, all right, in the center of a distribution, while very little data will fall out in the tails. So let's take a very basic idea here first. Let's talk about height of individuals. Let's say that we know there's an average height. Okay, we'll even collapse across gender here. We'll say that the average person is 5 feet 7 inches tall. All right, let's say that's average. And we've maybe heard a figure like this before. Well, you might think of where you fall on this particular distribution. All right, I fall over here on this end, all right, in the negative end. But there are certainly people over here in the positive end as well, right? But let's just sort of think of some basic statistical ideas. We have spread around the mean, all right? Something that we call standard deviations. How far do scores deviate from mean? All right, well, taking height as an example, all right, maybe we have some people that are, 5'9", maybe we have some people that are 6'1", all right, and then maybe over here, 3 standard deviations away, all right, 1 standard deviation here, 3 standard deviations away, we approach that 6'3" mark. All right, we might call anybody over 6 foot 3 inches pretty tall, right? Maybe even abnormally tall, right? Because all the normal people are here, right? And normal, we have to talk about the word normal while we're at it, right? Normal and abnormal in statistics means something very different than it does in our normal language. Abnormal means that it's not near the rest of the scores. It doesn't mean it's bad. It just means that it's abnormal, right? So we might call this abnormal. And if we go in the other direction, all right, and don't take any offense to this if you're in this abnormal range, again, because abnormal doesn't mean bad. It just means not normal. All right, so 5'3", 5'1", if we go in the other direction, I'm just moving in units of 2, all right? So then maybe anyone beneath 5 foot 1 inches we're calling pretty short, right, or abnormal, right? Kind of different than the rest, right? Most of the data is going to fall here. So when we do something like a hypothesis test, or what we're doing is we're looking for instances where we're usually here saying, okay, this is our population. All right, we're going to assume that the population is normally distributed. And if we get a sample of individuals and compare them to this population, where do they fall on this distribution? Do they fall close, all right, to the population? Or do they fall over in that abnormal area? right? Another way that we can think of these normal distributions, let me get another one going for us here, is using probability, all right? Is that most, all right, that term we're using, most people are going to fall here in the middle, and very few people are going to fall over here in the tails. So using statistics, we actually determine a certain percentage or probability that we've coined as abnormal. And it's usually 5%, all right? Alpha equals 5% or 0.05, and we'll sort of dip into this more in a moment. But what we're saying is, if we're going to look over in the tails for abnormality, we're only going to look at 5% of the most extreme scores. And if we want to detect a difference between groups, we would need to see one of our groups here close to the population and one over here. This would be a significant difference between groups. All right. So let's go ahead and hop back over to the slides and talk a little bit more about these concepts. Directional means you're predicting one direction, right? An increase or a decrease in a particular study. And again, we'll talk about this a little more, or you'll hear more about this in our stats review lecture. All right. Okay, so here we are. Here's our first kind of look at the p-value. So what is a p-value, or do we even remember this? A p-value is a probability, all right? So our hypothesis testing is based on probability, the unlikeliness that something were to happen. So the bigger the effect or an association that is expected, the smaller the sample can be in statistical terms. So this is sort of back to our sampling, that larger samples are better, right? Because we can detect more effects. But smaller samples, we can detect effects more efficiently in a smaller sample. So here we have a statistically significant finding is one that is large enough that it is unlikely to be caused by chance fluctuations due to sampling. All right, so that's a little wordy. All of this is a little verbose and difficult to unpack. So let's hop back to the whiteboard. Let's do a little bit more drawing here. Let me get a new slide for us. So let's go over a few of these topics here. Let me draw. Okay, so let's come up with a hypothesis, all right? We're all working on coming up with a hypothesis. Let's say, what do we want to do? All right, so we'll call this our alternative hypothesis. So we can have a null hypothesis that says, you know, there's no difference, no relationship, and we can have an alternative hypothesis that's our prediction. So let's say that we are predicting, let's see what we want to do. Let's say that we think that younger people, all right, younger people, and we'll stick with a college population. So let's say maybe for younger group, we'll say less than 25 years old. So younger people spend more time on screens. Okay, that's our hypothesis. We'll go ahead and think about this on a normal curve here. The null hypothesis would be that there's no difference. All right, here if we're comparing younger people and older people, the null would be that there is no difference between the groups. All right, so let's say that we have a normal curve. We're expecting this data to be normally distributed. That's an assumption that's often made when we're doing statistics. We assume normality of our distribution. Okay, so let's say that we have some population value. We're assuming normality, and we know that the average person, all right, the average person across all ages, the younger people populate, or the younger people sample that we'll take, is what we want to compare to the general population. So if you remember these terms, we have a sample mean. X bar is the sample mean. Mu is the population mean. All right, so let's say that for the population, we know that the average person spends, oh, I don't know, let's say 4 hours on screens a day. All right, 4 hours. So our average here, the center of this distribution, will be something like 4 hours. And let's say that there's a standard deviation all right? Sigma here is a little standard deviation. Let's say there's a standard deviation of 1 in the general population, okay? So remember, even if you're not familiar or don't recall what standard deviation is, it's just how far we stray from the mean. All right, so if 4 hours is the mean, if we go up in 1 hour units, we would have 5, 6, 7 hours. If we go this way, 3, 2, 1 hours. All right, so in this population, anybody over here, right, kind of over in this tail might be considered abnormal. Anybody over here might be considered abnormal as well, right, in this current day and age. So let's say that we grab a sample, all right, we grab a sample of younger people, all right, and the younger people ring in at, let's get crazy, all right, let's say that they're ringing in at 9 hours, okay, of screen time a day, which again, if people are doing telework, kind of like we're doing now, that might not be that unreasonable of a number, right? So let's say that's what we get. If we plot that onto this distribution, remember what we discussed, most people are going to be here, all right? Most people are going to be in here, statistically, right? We're going to see most people in here, in the center. Get that mess out of here. So if we get something like 9, all right, we plot this. This is way over here, right? This is way over here. This makes it seem like younger people do spend more time on screens than the general population, all right? And how we would actually determine this is we would look at the percentage. How likely was it that we got a score over here if this is true of the entire population? Well, using some general math here, we know that about 99% of scores are here. And we'll talk a bit more about this when we talk about the normal curve. So the likelihood of this happening was very little, all right? Less than 1%, all right, in this particular example. So just an idea of how some of these topics sort of work together. We're looking for abnormality. We're looking for cases where our sample seems very different than what was already known about a given topic. All right. And then in terms of the sampling stuff, all right, this is just sort of the law of probability. So the larger a sample we have, the more likely we are to detect an effect. The larger an effect is, the easier it is to detect it in a smaller sample. So if that's not making a lot of conceptual sense yet, I hope that you just hang on to those ideas, that the more individuals we have in a sample, the more likely we are to see significant results just due to probability, just due to having more data. And the larger the effect or an association, the smaller a sample that we can have to observe it effectively. And that's something that we'll notice in our own projects, is that even with small samples, we will be able to observe differences that are strong, ones that we would expect to be present. All right, so all of this that we're talking about is about statistical significance, right? If you find something significantly different than what was already known, or the null hypothesis, you have a significant result. And this is what scientists are often digging for, finding something that was previously unknown about the population or the data that was already present. And to make this more conservative, let's talk about this word conservative, we can push our p-value over, all right, make it harder and harder to successfully reject a null hypothesis. So let's go back to the whiteboard, all right, oops. Let's go back to the whiteboard. Let's get a new slide here, and let's think about this. And again, if you're feeling like, hey, I don't remember this stuff, my stats class hasn't got to this stuff yet, just stick with me on a very conceptual level here, all right? If you have a distribution of data, 100% of the data is here, all right? All of it's in here somewhere, all right? Some of it's over in the tails, most of it is in the middle. All right, but let's say that you're using an alpha value, you're testing for significance at an alpha level of 0.05, meaning that, let's say we have a one-tailed test. All right, that means you're looking over here, 5% of the data is over here. All right, these are sort of extreme scores or abnormal scores. If you find something over here, you have found something different than was thought to be true about the rest of this population, right? But what if, all right, what if we're testing something as serious as a drug that has a side effect of death, of sudden death? And this sounds extreme, but we do have medications that have side effects like this, right? Take chemotherapy and other cancer treatments. Sometimes in last efforts to treat individuals, they will be given medication that have very extreme side effects. So when we give somebody a pill that has a side effect as serious as death, we maybe don't want there to be a 5% chance that they fall into that group. So we can make our testing point more conservative. Maybe instead of 5%, we can change it to 1%, all right? We can test something so stringently that we can say there's only a 1% chance that you will see this side effect. And we can up it even more. You can change it to something like 0.01, right? Or 0.1% to make this even smaller. So that's what this slide is getting at here, right? Is that we're looking for abnormality, right? Something like a side effect. And we can push the probability of that happening off if we test using a more conservative alpha level or conservative probability. Remember that an alpha level or a significance level is just a probability. It's just the likelihood that something might happen. All right. So now how do sampling and statistics work together? Larger samples drive statistical significance. And we can fight this using something called effect size. If you think about a lot of our statistics, many of them require or use n, all right? Remember, n is our sample size. So sample size is often included in our calculations, but we know that sample size can influence significant outcomes. So effect size, if you take a look at this calculation here, we use means and standard deviations to calculate effect size. Means and standard deviations use n in their calculation, but effect size looks at something a little bit different. It looks at the pure magnitude of difference between whatever it is that you're comparing, right? Given our last example, it might be comparing a group of younger adults to older adults to see if there's a difference in the amount of screen time that they are spending. All right. Measures of effect can also be helpful in cases where we can have something like a correlation that comes out like this, that comes out to an insignificant effect because there's no linear relationship. So effect size can point us to a little bit more interesting of analyses. And if you remember back to correlations, let's hop back over to the whiteboard once more. All right, we can have strong positive correlations, all right, that look like this. All right, the trend goes upwards. We can have strong negative correlations that go like this. The trend goes downwards. All right, we use something called R values here. So maybe this is an R value of 0.9. This is an R value of 0.85. These are both strong correlations. But if we take a look back at this guy here, this would come out to something like 0. The statistic itself would say there's no significant effect. But if you take a look here, there's sort of a quadratic effect, all right, this U shape, meaning that there's a peak in the data, all right? This is between leisure satisfaction and work satisfaction. There's sort of a sweet spot where these two things meet, right? If you're completely satisfied in your work, you might not be as satisfied in your leisure, right? If you're completely satisfied in your leisure, you might not be satisfied at work, all right? So this is a little bit more of a complex relationship, and this is why we have to also look at the data and visualize the data, which is why we're starting to practice that here in class. And I think that correlations really illustrate this well. All of these graphs have the same correlation value. These all came out to a moderate correlation of 0.5. So it's important to look at more than just statistical significance or the measure of a statistical test, because sometimes there's a little bit more going on. We can look for trends in data visually. So the conclusion is, all right, psychology is complex. It's difficult. When we want to make decisions and we want to make generalizations in an accurate way. So we follow a few rules of thumb to do so. We think about the limitations of generalization, and in fact, we'll write about the limitations of our own studies in our paper. We include it in the discussion section of our paper. We have to think about the limitations placed by the sampling methods used, and the limitations placed on research by statistics, which I think is an interesting topic to start diving into in this class, which is that statistics help to guide us, but they're imperfect, right? There are errors in our statistics, and we have to take them for what they are, right? We have to take them as suggestions and suggesting different trends and something that needs to be tested again and again to confirm validity. All right, so I hope we enjoyed this dip into statistics and generalization and decision making. Remember that this particular topic sort of goes together with our statistics review, our sort of overview of the main types of statistical tests, so make sure that you're giving that a watch as well. And I will see you over on the next one.